Make very short. A couple of years ago, we started simulating, using me scattering, simulating the horizon glow that, the putative horizon glow that Latte UVS might. And others will cover. This measurement is under scrutiny. It's a lot higher than you can explain by meteoritic ejecta or by electrostatic lofting mechanism. I won't spend any more time with that. The real crux of this study is the fact that both LAMP and UVIS are now going to carry out new searches. Okay, after some 35 years, now you're going to have very sensitive spectrometers looking at the limb under full sun and presumably from within shadow, and create a whole sensitive new data set. An additional advantage is this broad spectral coverage and spectral discrimination. And that's something that Apollo didn't have. I mean, these were photometrically calibrated, but it was effectively one broad filter. It was just film that was illuminated and pre- and post-flight calibrated. How do you know when these instruments detect excess light? How do you know what they're seeing? You could get a sort of a first-order estimate of the dust abundance, but the amount of the quality, given the quality of the data, what's in there, there's information that goes far beyond that. So it's the obvious thing to do is to create realistic scattering models and ask the question, for starters, if we put an Apollo 15 dust exosphere up there, what does LAMP and what would LAMP and UVS see? Bill's covered this pretty well a little while ago, but I just added to the sector figure here. Let me just cover quickly what the chronophotography, how that was carried out. The command module, as it goes into shadow or comes out of shadow, takes a series of photographs, which is the 70s word, and in each of those photographs, McCoy looked at those, and he picked out intensities at discrete points from those photos. And here I show those intensities for several different coronal sequences plotted. If you look at the point is, if you look at surface sunrise, you see excess brightness. Neither of these surface sunset cases show any obvious excess brightness. How do you know that? You first have to overplot the coronal zodiacal light, sort of a reasonable range of those values, min value, max value, and I've done that. Here it's questionable at best. Here, this is the log scale. Here you have a clear excess, clear brightness excess, and this is what spawned the McCoy model 0. What we've done recently is take another look at that, and we realize we've got excess brightness quantified at several distances away from the limb and at multiple elongation angles. You can invert that then given the error bars to retrieve dust concentration versus both height and tangent point. There's no time to get into the model results. There are a bunch of the retrieval results are a bunch of profiles. But the important thing, I think, to note is that the McCoy value, this is a number to take away. McCoy value of 0.01 per cubic centimeter at 10 kilometers holds up. The 10-kilometer heights was a well-sampled region of those measurements, so it's a pretty confident retrieval number. Above and below that, the error bars just get very large very fast. But nevertheless, we have this number, and we also have, this also gives us a dust model that we can go ahead and use for our modeling. Real quick, let me cover the spectrometers. Rick Elphick has already explained this in detail, but I do want to point out that here's the lamp. Lamp extends down to some 60 nanometers, and if you treat these guys as one very broadband spectrometer, you have spectral coverage that goes from 60 nanometers all the way up into the near IR. And that brackets the scattering properties of submicron grains. So the scattering properties will vary dramatically. That means you have if you consider these together, you have a very good diagnostic of size and shape. Another thing to point out is the orbits of these two instruments they're about the same height, so the vantage point, the look direction will be from will have about the same will be from about the same point. Both of these guys will do limb measurements, both in full sun, meaning that they're looking at side scattering of the grains. That's important, and also from within shadow, meaning that they're looking at the small scattering angles. Comment on this, well, the in-shadow case is a little bit problematic. It has to be orchestrated with lamp, but it's being worked. I thought I'd throw this in. Kurt Rutherford gave me this still animation frame, and I jazzed it up a little. This is the lamp animation frame. I jazzed it up a little bit. I showed the image scales compared the image scales for both of these instruments. Lamp is a slit spectrometer. UVIS is a point spectrometer, but it has in its limb occultation mode, it has a fixed point. There's a fixed pointing plan where it can follow the sun down, so you effectively make it a slit spectrometer, so you can compare almost apples with apples. If you have a high altitude dust exosphere with a scale height of something like 5 kilometers, 10 kilometers, or 15, that exosphere is well sampled by both of these instruments. So in terms of spatial resolution, they will do a good job. Okay, now how do we want to try to simulate the spectrum that these instruments will see. How do we put that together? We gave up Mies scattering some time ago. Mies scattering refers to scattering by spheres, and we don't know what the shape of the lunar grains will be. They could be they could be a range of things. Dennis, Richard, and I, and Tim, the last couple of years, have been looking at multiple grain shape models, and Dennis calculated the scattering properties of those grain shape models. We take them, we put it into the instrument simulations. We've been doing this game now for a couple of years. This is kind of our collection at present. They're based on ultrafine grain Apollo samples, plus we've added some oblate and prolate shapes in order to expand our taxonomy of dust shapes. The idea here is that when we calculate these, we represent these simulations in terms of envelopes. We don't just take a Mies sphere and say, okay, that's probably what you're going to see as a function of wavelength. You want to sort of delimit the possible range of real particles. A couple of other recent augmentations to the models. Optical constants really determine what the scattering does, and we had to expand our spectral coverage, our spectral range of the optical constants we were previously using just a fixed value, and solar spectral radiance from source. Okay, here are limb brightness results. two vantage points, from the shadow vantage point and from full sun. One looks at forward scattering, the other one looks at side scattering. Here's our envelope of shapes. Here's the lamp spectral coverage down here at very short wavelengths. Here's UVS that goes on out to past 800 nanometers. First thing you notice, the scattering, if you use an Apollo 15 type dust exosphere, it should be very bright, okay? Much brighter than the detection limits of these instruments. Another thing to notice is that, and this is all, it's hard to explain right off the cuff, the consequence of the phase function behavior, but you get a big intensity contrast. If LAMP looks at forward scattering and compares that with a side scattering result, there should be a big intensity difference, but not much. UVS, on the other hand, should not see much intensity difference. Okay, let me move on. Even more interesting are dust colors, because now the color information is what now gets away, not just from the abundance, but tells you a little bit about grain size and shape. And what I've done is treat two size cases. Something a little bit smaller than our canonical 0.1 micron grain, and then another radius about twice the size. Interesting thing is, for tiny grains, kind of interesting, they all line up. The reason is they look like Rayleigh particles out here. You come up, you go through everybody goes through the first maximum together. That sort of follows the first maximum of the scattering coefficient, Happiest plotted, things like that. If you move to larger grains, if we in fact have larger grains, then the situation is a lot more interesting. Well-ordered grains, they move, that same peak moves out to longer wavelengths. But then the shape information starts to become important. More loosely bound grains will have sort of a messy, disturbed shape. So it's going to be, it's a little bit convoluted. It's not a nice, neat result. But it does tell you that if you plot dust colors, I'm sorry, I should have mentioned on the beginning of it, that's the dust intensity and taking out the steep solar spectral slope. That color information gives you grain size and possibly shape information as well. It's an interpretation problem. Okay, just some final remarks. To sum things up, LAMP and UV should observe with big signal to noise, given the fact that they're very sensitive instruments. If you're going to try to simulate those, you really should use multiple grain shapes. Dennis uses a discrete dipole. Me models you're looking at just one little tiny window in the space of possibilities. Dust colors should be a grain size giveaway if you analyze the data properly. The bottom lines are the LAMP measurements supported with these kinds of models should constrain the concentration, grain size, and even shape. And I think that this is a good segue into the next to talks later on in this session. So thank you very much. Yeah, you're right.
Dave, I didn't catch on those spectra that you showed. Mm-hmm. Does that not include the CZL, or does it include for forward scattering?
Well, no, those are just there's no CZL in those simulations.
Right.
Okay.
So
that's a dust scattering. So in the forward scattering case, you're going to have to contend with CZL.
So even though you're saying these things are bright, they're also bright against a very, very, very bright background.
They are. At long wavelength, CZL you really have to untangle it. It dominates the spectra. I mean, I didn't show it; it's just overwhelming today, but. At LAMP wavelengths, it's very, CZL just goes away. I asked Paul Feldman if it would contribute, around 180, 190 nanometers, and he didn't think so. He had taken a look at that before. So it's only in the UES case that's a problem.
Any other questions? We have time for a quick one.
Sort of a comment. So I've tried to do some similar calculations for measuring the density of the dust cloud being blown by the lunar module during landing. And I wonder if I could get you to critique my paper for me, please, and if we could compare notes, because
compare
at present we're just using me scattering, and we know it's not
Yeah,
that accurate.
okay, well, let's say Dennis and I together have been putting these, we've been creating grids of DDA models. Obviously, it's not, DDA doesn't give you a nice analytic solution like me does, but sure, we can, you can talk to either of us and we can get those grids to you. There's the finite coverage in the grids, phase space in the grids, but we'll get them to you.
Okay, we're going to have to move on if we need to stay on